so yeah, today we're speaking about switch statements, which are kind of a hard thing to handle in when you're doing a decompiler. But let's dive into them. Switch. So first of all, let's look at how the compiler lowers them. So imagine you have a very simple switch statement, switch x, case 0, 1, 2, and then you have the default case. In this case, they are all returned, but yeah, let's just assume it's O0, and let's look at the assembly. In x86, it will look something like this. Basically, you will have, let's suppose that array x contains the switch condition, what before was x. And first of all, it will compare it with the highest value in the list of cases you have. So the highest value here is 2. So here it compares it with 3. And then it performs a jump if basically jump if greater. So you take the x, the switch condition, you compare it with 3, and if it's greater than 3, you jump to end. This is basically how typically compilers handle the default case. If you have a dense set of cases, there are no holes, and you just check, okay, is the value of x greater than the highest value in any case label? If so, we jump to the default case. So end here is basically the default case. And then otherwise, so if x is lower than 3, we basically use a jump table. So here you can see that we are doing jump, and then we are loading from memory from a specific address. And this address is the address of a jump table that we will see in a second. So this is, let's say, some memory area in .row data. And we take the base address of the jump table and we add array x multiplied by 8. So at this point, we know that array x is lower than 3. We multiply it by 8 and we add it to the base address of the jump table. We load what is there and we jump there. Okay, does this make sense? And the jump table is rather simple. Here you have, I think that the third one here, I should not have it here. Yeah, so basically, this is a bit wrong, but basically imagine that you have quad 0, 1, 2, and basically these are the entries of the jump table. So the idea is that the jump table contains 3 elements. The first element will point to 0, the second one will point to 1, the third one will point to 2. Okay, so basically if, again, array x is lower than 3, you load from one of these values, and these values contain the address of the basically basic blocks representing the case of the switch, and yeah, you jump there. Why do you need to multiply it by 8? Because array x is the index of the entry in the jump table, and each entry of the jump table is 8 bytes wide, which is the size of a pointer. Does this make sense so far? The concept of jump table, sensible. Okay, so currently, so there are 2 problems with this. First of all, you need, at lifting time, so let's say at the beginning of our decompilation pipeline, you need to be able to correctly recover the CFG of this thing. And this means that after this jump, you need to be able to statically, so just looking at the code, prove that this jump here can jump only to here, here, or here. Okay? Because if otherwise you consider just a random indirect jump that can go anywhere, you don't have an accurate CFG, and it's hard to be precise in doing all the rest of the things that we need to do. So the first thing in the pipeline is be able to devirtualize, let's say. So this is a virtual jump, let's say an indirect jump. And the first thing that we want to do is to be able to understand where this jump can jump. And we have spoken about this in the past. This is the role of AVI, Advanced Value Info, and all that stuff, and we'll go through a bit more of this. But basically, the idea is that AVI is smart enough to know that if you get here, array x will be contained between 0 and 2, okay? And then, basically, it will try to materialize all the possible values that this expression can assume, as knowing that array x can have value 0, 1, or 2. And this also means reading memory. So statically, we read memory, but that's fine because it's read-only memory. if this makes sense. So first thing we need to do is devirtualize them so we know where it jumps. And we're rather good at it. But then there's another problem. Let's look at how the final decompiled code looks like. So we decompiled the code before to something similar to this. We have if argument array x is lower than 3, okay, which is the first comparison with the JA that we saw before, then switch on, and there's a pretty complex expression here. And also the value of the cases, it's not very nice. Why is that? Because basically we are decompiling also the access to the jump table. So all this part here is basically represents, let's say, the starting address of the jump table. And then we index into this jump table using argument array x, shifted left 2 positions, which is it's the same as multiplying by 8, and then there is a mask. I don't remember why there's a mask, but let's ignore it for now. So as you can see, this is rather similar to what happens in the assembly. You have the load from the jump table, you have the if statement, but we cannot say that it's very close to this. We would like to see something closer to this. And that's what today's talk is about. So again, first thing, before we speak about default case, which is a second topic, let's say, first of all, we want to go from this to just focus to have the switch just focus on argument array x. I hope that you agree that this would be an improvement in terms of readability. And I come up with a solution that I'm gonna propose. So first of all, the idea is let's iterate over all the switch instructions that we have in LLVM-IR. So imagine basically we're gonna try and find this switch instruction. And what do? First of all, we get the switch condition. Maybe the method is not called get condition, but this is pseudocode, okay? So we get the value, the LLVM-IR value that is the focus of the switch statement. And then we use this thing, which is called value materializer. Value materializer is basically the new fancy name for what AVI did. So you can do value materializer get values for, and you give it a position in the code and the value. So basically you say, can you try to understand what values this value can assume, just doing your analysis. So condition is the value we're interested in, but we also need to tell him in which place, because the same value could, you could be able to prove different things about a certain value in different places of the code. For instance, if you have a value before an if statement, maybe you cannot say anything, but if it's after an if statement that checks if that's lower than 3, you can say different things. So you ask for information about an LLVM value, and you give it some context. What place in the code you want to know information about. And then there's quite a bunch of other stuff that I'm cutting out here. So value materializer gives you back a value materializer object. Value materializer get values for gets you an instance of value materializer, which has some nice methods. Let's see which one we are interested in. First of all, you can ask him the data flow graph. Okay, so to go back on something concrete, something practical, if you ask about the switch condition of the thing before, you will get a data flow graph that basically looks like this. And by the way, value materializer can actually emit this kind of graphs. It's pretty nice. So you start from the switch condition, and the data flow graph, basically, it's going to be a small AST-like. It's not an AST, but it's similar. And first thing you will find, let me go back. Yeah, this is not exactly like this, but I guess that you can relate it to it. So you have you sum the starting address of the jump table and the result of the multiplication by 8 of array x. Okay, so this is the expression of the switch, and we know that array x value materializer is also able to find constraints on some nodes of this data flow graph. And in particular, it's able to prove that array X, in that specific point of the program that you ask for, is constrained between 0 and 2. And that's why this node is red. Does it make sense so far? Basically, this is what you're switching on, and it's the result of some computation that is add the address of jump table plus the result of multiplication of array X multiplied by 8. If we go back to the original assembly, this is pretty much what's going on. Actually, this is wrong. There should be also a load operation in the middle. Okay, this is how the address of the load is computed, but here you should have a load operation. Sorry. So basically, this is what this data flow graph is. And what do we do with it? First of all, we make some sanity checks. Value materializer does not only provide you with the data flow graph, but can also tell you the value you ask for, what are all the possible values that it can assume, according to expressive power. For instance, in this case, we know that array X is constrained between 0 and 2, so value materializer is able to compute this expression for all the possible values of array X, which are 0, 1, and 2, and it will give you the result of evaluating that expression for the possible values of this value on which we have constraints. Let's say they call it the red node. And so if you try to enumerate all the possible values, we want to make sure that they basically match the current set of labels of the switch statement. Okay, this is a safety check. Basically, at the beginning of the pipeline, we devirtualize an indirect jump and we created a switch statement. And now we are later on down the pipeline where the IR is much better looking and simpler. But we are rerunning basically the same analysis because originally the devirtualization was performed using exactly the same tool, value materializer. But just as a safety check, we want to check that the things that we discovered back then are the same things that we are discovering now. So we ask value materializer to give us all the possible values, and we check if they are basically the set of values of the case. To be more specific, basically we are checking that we know that argument array X is constrained between 0 and 2. We compute all the possible values of this expression. We ask value materializer to compute for us all the possible values of this expression. And then we simply check that the set of resulting values match the set of case labels that we have in the switch. Does it make sense so far? If there's something unclear, please stop me. I see thumbs up. Okay. So basically, again, compute run value materializer, take the data flow graph because it's nice to look at. Here's the data flow graph. Check that it's still coherent. If not, something went wrong. We might abort, but then Jack complains. So in this case, we just bail out, and it might be interesting to inspect why things do not match. But this is just an optimization, so we can also not do it, and it's not too bad. So after that, I will not spend too much time on this, but basically we identify the red node, and we assume there's just one red node. The red node basically represents sort of the free value in our expression, in the sense that it's a leaf of our expression on which we have some constraints. Okay, so basically, ideally and in practice, it will always be argument array X, because while this expression is rather complex, and maybe the data flow graph could also extend beyond argument array X. The nice thing about argument array X here is that is the LLVM value on which we have the constraint. Okay, so it's a spatial node. The red node is the node on which advanced value info was able to find a constraint. And that's our, let's say, starting point for everything. So yeah, we found the red node. If there's more than one, we bail out. And then basically at this point, basically the red node represents what we want to use as a new switch condition. So at this point, we want to rebuild the switch statement, but instead of starting from the data flow graph that we saw, we want to just have it become basically a switch on the red node. But before doing this, doing this is rather easy. You just do switch, change the condition, and use the value associated to the red node. But you cannot just do that. You also need to rewrite all the cases of the switch, right? And so here is what we're doing. Basically, we take the red node and we go through all the possible values that we have proven it can assume, all the set of possible values that it can assume according to AVI. And we use the data flow graph. We materialize for each value, let's say, of the red node, we materialize it, and we get what basically was the old label. Okay, so originally the switch is expressed in function of the result of this expression. And now we want to turn it to be expressed in function of this node. So the idea is, let's try to compute all the possible values. Let's get all the set of values that this can assume, and let's run this expression, and we get the result. And for instance, one result should be this value, right? We verified that before. We verified that if we compute all the possible values of the data flow, starting from the constraints we have on array X, we should get all the cases. So we verified that basically if you compute all the possible expression, you will get all the possible cases. So the idea is that for each of the old values of the case, we want to know which value of argument array X corresponds to. And this is more complex to say than to implement, because basically for each possible value of the red node, you compute the DFG, you will get the old value, and you just note down that the new label, for instance, for case 0, here the first possible value of the red node will be 0, the second will be 1, the third will be 2. You say, okay, for value 0, the basic block I have to jump to in the switch I want to rewrite is basically the block that before, currently, the switch was jumping to in case you got the value old. So again, the idea is that we're computing a map that says when argument array X has value 0, you want to jump at the block where the old switch statement was jumping in case you get this value. So basically, we are mapping the values that are expressed with respect to the current switch condition in terms of the new switch condition that we want to use. And then basically, you're basically done. You change the value that the switch statement is working on, which is the one associated to the value, and then basically use this map that we created here to recreate all the cases. And that's done. So does it make any sense? I feel like I've lost some of you. So if you have any questions, please interrupt me. Ivan, go ahead.
What about the wrapping if? Do we also remove it, or is there some kind of devoted stone that doesn't let us, like the original if AX more than 3, then like can we also remove that if, or does it have to stay?
That's the next part of the presentation. This was mainly focused on going from this to this.
So one more question. Do we care about cases in the assembly that goes in backward direction, like is, I mean, this control flow is already constructed.
Just me, or we lost George?
Can you hear me?
I missed it too.
Yeah, George, if you could repeat, because I lost you.
Yeah, for a while we lost you.
So is there something specific about this algorithm? Okay, if the case, okay, the value of case goes in the assembly in the backward direction, like a
It's like a back edge, you mean?
yes.
Well, no, not really. I mean, we're just. I mean, the AVI has its own expressive power. So, you know, sometimes maybe it will stop computing the data flow, and it doesn't, you know, it doesn't. I don't think it handles fees in the data flow or stuff like this. It has a certain limited expressive power. But as long as AVI gives you a data flow graph and you are able to find a single node for which you have a reasonably small set of constraints that match what was, I mean, that if you enumerate all the value, it matches basically the old cases. You're just basically, you're not changing the control flow in any way. You're just skipping this part of the computation, let's say, and changing the cases of the label. But the edges of the control flow graph do not change in any way. You just change the value of the case, and you basically skip this part of the computation. And you create some dead code, let's say. Sorry, also all of this goes away. And so the semantics, I think they should be preserved, unless you expect, for instance, the memory loader to segfault. But of course, since we proved, since AVI was able to prove that that memory load is going to access a very narrow area of memory, and you know that is going to be mapped, I think that is fine.
Okay. So we are just simplifying these expressions. Okay. I had in mind some changes to control flow graph, but yeah, okay. If we don't care about it, it's fine.
Yeah, we made some changes in a second when we try to get rid of this, but that's a bit more work in progress, and I'd like to talk about it in a second. Other questions? Okay. So let's assume that then we did this. Okay, so we went from this ugly expression to something like this, but we still have the if statement, as Ivan hinted. So what about the default? Can we detect it? And let's go back to some more examples. So consider this new switch statement where you have case 0, 1, 2, and default. Okay, we will decompile it as such, basically. We will again check if x is lower than 3, then we will emit a switch statement with no default case, or let's say that the default case is abort. And then in the else, we have what was originally the body of the default case. Okay. This is not perfect, but it's not too bad, right? I mean, it's not ideal. You would like to see the default case, but it's not terrible. I mean, it's not critical. Let's see another example where things get critical pretty quickly. It's the same example as before, but I removed the case 1. Okay, so this was how it was before. Case 1 return of 431, and now it's gone. So what does happen then? That case 1 falls into the default, right? But compilers are quite smart, and they try to be smart. So even if you have a set of cases that is kind of dense, 0 and 2 are not too far away, but there are holes like 1, you still want to use jump tables because jump tables are rather fast. And so what do? You put in the jump table, you still use the jump table as before, but for case 1, you just, instead of putting the address, of the case 0, you put, or case 2, you put the address of default. So the jump table still exists, even if in the switch statement there's a hole, but in the jump table, simply for the entry corresponding to the hole, you put the address of the default block. So to be more explicit, this is the CFG that we get. So first of all, we check if x is lower than 3, and if the answer is no, we go to the default case, and that's just as before. Otherwise, if x is lower than 3, we switch on 0, 1, this is the new edge, and 2. So in case, and this is done with a jump table. The switch basically represents what in assembly was the jump table in this case. So when you switch on 0, you go to the case 0. When you switch on 2, you go to the case 2. But when you switch on 1, you're still using the jump table, but you go here. Does this make sense? Compilers really want to use jump tables because the alternative would be to make a lot of if statements, let's say. Giorgio, go ahead.
Yeah, that was actually my comment. Yeah, there should be like a magic value of the, for checking the number of cases in the switch. And yeah, I think the compilers switch between using branches and jump tables, especially on the target, actually on the back end, because some targets are not that good in using jump tables. So yep.
Yeah, I mean, this is a kind of a toy example. Maybe in this specific case, the compiler could use switch, if statement, and don't use jump tables at all. But for the sake of the example, I mean, I'm sure that if you have 100 cases and you take one away, it's probably still want to use a jump table. And this example actually comes from a concrete example that we found, and this is why all of this started. So it's something that happens, but you're right. And there are heuristics on whether you want to use a jump table or not. Other questions? All right. So basically, this is how we decompile this stuff. If x lower than 3, then we go to the jump table. Let's go in the false case, the false branch. We have return 1, 2, 3, which is our default. But what if we go into the switch? Case 0, return 42, as expected. Case 2, return 69, as expected. But for case 1, we have go-to default case. So we emitted a go-to. Now, if you know something about Andrea, you know that we are not emitting a go-to, but we are duplicating code. But yeah, for the sake of simplicity, let's say that here I used a go-to to explain that this is problematic. And so in truth, again, we duplicate code, and this is not nice because it's not one of the nice situations in which we want to duplicate code. I mean, ideally, we never want to duplicate code, but in this case, you look at this piece of code and you say, wait, there is something we could do. We could detect the default case and basically have just one copy of this block as a default here, and that will save us a copy. Would do. Okay, now we have an algorithm for doing this, and it's not, let's say, very, very final yet, but I want to try and give you the gist of it. So the idea is to use, again, AVI, or let's say someone able to provide you constraint on the value of x in a certain program point to do this. You go from basically, put it simply, you go over all the basic blocks and you look for if there is a basic block for which there is a set of incoming edges that basically can represent the default of the switch. Okay, and guess what? Let's try and focus on this one. Okay, this block has two predecessors, one coming from the switch and one coming from somewhere else. Now, if we were to put constraints, the set of constraints that we know to hold on x on the edge, here we will say x is lower than 3, right? On this edge here, on the no edge. While on this edge, we will know x is exactly equal to 1. Now, the idea is to find a set of incoming edges, and in this case, it will be just one edge, that if you consider them together, basically represent the complement set of all the values that are explicitly handled in the switch. So let me be more specific. The set of values that are handled in this switch statement are 0, 1, and 2. Right? The complement of this set of values are all the values that are greater than or equal 3. And this is exactly the constraint that we have on this edge. Okay. Now, there might be more complex examples where it's not just one edge. You know, sometimes you have weird things, you know, maybe, yeah, maybe later I will show an example of a more complex situation. But like if you have switch statements with, you know, case, I don't know, 4, 5, 6, and then you have case 10, 11, 12, the compiler might try to make two jump to have a single jump tables to manage these two disjoint ranges, and then you will have more complex if before you will have multiple if statements. Okay, so but let's consider a simple situation. So we identified a basic block that has a set of incoming edges, in this case only one edge, that basically represent the complement to what the switch statement that you're looking at actually handles explicitly. Okay, well, that's our default block. Okay, and so what do we do then? Okay, we identified a good candidate for being the default. But what do we do now? We need to make a transformation on the IR that actually, you know, makes it so that we do not emit the if x lower than 3, but instead just emits a switch with default. And the idea here is to, I don't know how to say it, but basically staple this edge to the switch. So imagine that you staple this edge here. Maybe I can draw it real quick. Let me make another slide. Here on the right, you can see it. Basically, what I mean is that we want to go from okay, that's more like it. And then so this is what we want to do. Okay, this is the transformation we want to do. Maybe let me put it here at full screen. We want to go to this situation. So there was this edge, the no edge. We want to basically split it so that it first goes here, and then we have a new edge that goes from here to here again and represent the default case. So basically now, yes and no both go to the switch. But we also added a default. Now, there's a small note here to make that I'm skipping over. But basically, the whole idea is that you staple this here, and that's safe. Why is it safe? Because basically, here you had a direct edge, and now instead, it's still kind of a direct edge, because you first go here, but you know that if you will go here, then you will not take any of these 0, 1, or 2 edges, but you will for sure take the default edge. So you made the control flow graph a bit more complex, but you're not changing the semantics. Okay, if you staple, I should not point to the screen, I should use my mouse. If you staple no here, you are not changing, I mean, all the execution paths will be the same, because if you were to take this edge, what will happen here? Well, you will go here, but if you are taking the no edge, you will not take 0, you will not take 1, you will not take 2, you will take the default branch, because we've been able to prove that. We've been able to prove that the no edge will always go, basically completely represents the default case. Are you persuaded of this? Anton says, so you combine it. Yeah, exactly. I'm willing to do one extra step, but first I want to see if I've been able to persuade you that this is kind of okay. Okay, let's assume that I persuaded you. Now, I cheated, okay, and let me tell you why. Because, yes, so the switch, actually, you know, it does not only do the switch, but it also performs a load, right? So we are changing the semantics here, because before, in the original code, you would run the load instruction, which might segfault, right? Only if x was lower than 3. You know, let's say that this was loading, you know, jump table plus x multiplied by 8. Okay. Now, this was supposed to run, this load instruction was supposed to run only if x was lower than 3. And so we are changing the semantics here, and we don't want to do that. So the actual transformation we make is to split the switch statement into and we do like this. Sec. Okay. And I need to fix one more thing. Okay. Okay. So we split. Why does this say? This still says which two? Anyway, so we split the basic block that contain both the loading and the switch in two, so that basically in this new switch block, we only have the switch instruction and nothing else. Okay, so basically now what do we have? We have if x is lower than 3, we perform the load. Otherwise, we go directly to the switch, and then we are 100% sure we always take the default case. Okay, so in this situation, we are not running this code in any other path compared to before. Okay, and what is the nice thing? The nice thing is that if this thing is not there, you know, you remember the load. If we go back, basically the whole point of the previous part of the presentation was to get rid of that load, right? Here we were doing a memory access, and after that, instead, we don't have any memory access. Okay, so the idea is that if these two transformations are combined, what will happen is that this block here will be empty, or it will not have any side effect. You know, that doesn't matter. Maybe there will be some computation, but it won't have any side effect. It will be, you know, just additions. So the optimizer will be able to make this if disappear. Okay, if this load is not there, if in this block you only have things that do not have side effects, then the compiler can simply move the code there, and basically then you have an if which goes in both situations to the same block, and so you can just remove the if. And then basically you get to, let me do another graph real quick. You get to simply recheck does nothing. You don't go to but you go directly to and this no longer exists. This no longer exists. So you go to this thing, which is, you know, exactly what we wanted, right? Okay. Questions. Let's see if this makes sense. Ivan.
Yeah, okay. If we live in a perfect world, it makes sense, but self-defined code is the thing. So what if some other function before this one overrides the jump table into something it wants to? So can we really rely on jump table be constant every execution?
Well, obviously we're making some assumptions, but typically, and I think we check this, we use, so when we run AVI, we have a so-called memory oracle, which is basically a black box that you can ask in, okay, what is going to be at this address at runtime? And basically this oracle looks into you know, the model, what we have loaded from the binary, and we go check in the binary what is there. But it will do only if the segment containing an address is read-only, right? So it is reasonable, it's very reasonable, you know, to expect, I mean, for a static analysis tool, basically the binary is telling you this is not going to change, you know? And then it's reasonable to assume, to basically do, let's say, constant propagation, because it's explicit, it's in raw data, it's explicitly stated. And basically all jump tables end up in raw data because there's no reason, actually, it's kind of dangerous for them to not be read-only. So I think it's rather safe to do this. Did I answer your question, Ivan? Okay, Andrea?
Sorry, I got a bit lost when you explained the criteria with which you elect the candidate block for being the default. If you go back, I don't recall the number of the slide. There, I guess, yeah. So you search for a block which has incoming edges that are the complements of the values handled by the switch.
Yeah, so basically, if you ask your oracle, on this edge, what are the constraints? And if you have a set of incoming edges, again, in this case, it's just one edge, the no edge, that is associated to all the values except all the values that are explicitly handled in the switch, then that's a very good candidate. It's kind of the definition of default, right?
So even if you have multiple, let's say, voids in the multiple cases that are actually not there in the original switch, you still get the complement property to hold, because those are handled by the switch, and you can do this, say, also for multiple, say, for handling multiple holes in the range of the values covered by the switch. Okay. I was maybe distracted. I didn't get it perfectly during the presentation. Okay, thanks. Checks out.
Yeah, it does make sense, because you have to think that the cases that we saw in our switch are not the cases in the original switch, but are the cases that are induced by the indirect jump. So by the indirect jump going through the jump table. So they are always dense. You know, jump tables are by definition dense. You cannot have holes. So if you have a jump table, you will always have a starting case and you will go one by one and there will be no holes. So the case one is there and we don't care about what was the original code. We just need to be able to ignore it, you know, because the case, one thing that we attempted before with while I was discussing this with Pietro is to consider the constraints that hold in the whole block, you know, not considering the incoming edges. And in this block, the constraints are 1 or anything greater than or equal to 3. But then it gets a bit trickier. So it's important to, because you don't know where to staple. You know, the stapling thing, you cannot staple including 1. Because then what do? You do a loop, it's not nice. So you need to identify a set of incoming edges that, and in this case, again, it's just 1, that if you bind them together and you staple them to the switch, then those set of edges represent default.
Yeah. Now it's clear, I guess. Yeah. Thanks.
Okay, thanks. Ivan?
Yeah, I have one more question related to what Andrea just asked. I passed some code into the chat. Like, what if we have something like this? As far as I see, this final and default basic block analyzes incoming edges. So what if we have some conflicts? Like, for example, what if we have multiple points in which something based on X jumps to it? How do we like discard the cases like this?
Okay, I should really draw the control flow graph in order to be able to answer intelligently. Let me see if I can spot.
The point is,
so you have an extra, yeah, but that extra edge. Modify value. Okay, the point. I will assume. No, wait, you cannot do modify value because we are in SSA. So in SSA, the X before modify value is a different value from the X after. So you have if X greater than 1, and that's one SSA value, X is one SSA value. Then after modify value, which I assume is some assignment or something like that, you have if X lower than 3, and that's a different SSA value. So they are different. They are the first comparison. It might be useful, but it's we will not consider it.
Okay, so let's say modify value is not there. So we have two contradicting checks. Let's say, what would happen in this case? Like for example, in this case, it's switch once in case 0 go to 42, else go to end. Like the other edge is like does nothing because we already checked that.
Okay, let me check. Yeah, so you're saying that basically.
What if we have multiple checks that check like contradicting things and then all jump into an end or something like that? So we cannot clearly say, hey, this is the default because we have multiple.
Pietro, you want to say something? In the meantime, I can try and draw the CFG.
Yeah, sorry, I was muted multiple times. I mean, I think that the case that Ivan pointed out with if you remove the modify value, you have to remember that we are optimizing things. So you don't really have, that can't happen because if you have if X larger than 1, for example, the case 2 will disappear, I guess. I mean, the compiler is able to can scramble up the switch however it wants, and so we have to to give a proper answer to this question. We have to understand how the switch would really look like after the optimizer has done simplified CFG with the new constraint, or maybe it stays like that, but it's not obvious to me at first sight, because case 2 in the switch becomes dead code. And so what the control flow looks like for real is not obvious to me.
Is this what you have?
One more if, but yeah, pretty much.
There is an if x less than 3 before the switch.
Like it was your example, but with one more if on top.
Okay. Ivan, come on, what kind of...
it wants quotes, I think.
Okay, so we have 3, switch, label, yes. So it should be something like this, right?
Yeah, pretty much.
Okay, so let's see what are the constraints here. I mean, so we don't have the default edge though. This edge is not there. We have instead switch one, switch default with a label 1.
Yeah. You called it
Goes
end.
to end.
Wait, what? End, okay.
Okay, so here, what constraints do we have? We have that x is greater than 1 or so. I mean, it kind of still works, you know, you just ignore this edge. This edge stays as it is, but for this one, I mean, for this incoming edge, the constraint holds. I mean, the statement I did before works because here it's x is greater than or equal 3, and here the switch has 3 cases which are 0, 1, and 2. So you will simply ignore this edge, which might still lead to some not nice code, but your input code was not nice either. Okay, there was a goto. So it's not like that we're missing some pattern that is artificial from the compiler. There was a goto in the original code, so it might be bad. We're okay with admitting bad code. But this one, instead, has the right constraints. So we just staple this one, and we should get a nice switch, I think. I can put constraints, because basically no here would have the constraint 3inf, and through this one will have the constraint 2inf, but it doesn't matter because this is when you look at the set of predecessor edges, you have to find a set of incoming edges that satisfy a specific condition, and this set, in this case, there is a set of edges, and it's the set composed only by this incoming edge. Do you agree, Ivan? Pietro, go ahead if you want to speak.
I disagree because if you are in that edge from x less than 3 to end, you must have taken the edge from x greater than 1 on the false edge. So in the block,
You're right.
Less than 3 is it's like it must be less than or equal to 1.
Yeah.
So it's basically just 2.
Yep. So yeah. So
okay, but then in this case we will do nothing.
Exactly. But my point that I stated before is that if the compiler is able to prove that in the blocks x less than 3, x is actually less than or equal to 1, it's just gonna remove that and then or change that, and the switch will lose some cases. I mean, the entire control flow graph will look much simpler than this, and we might be able to come up with good decompiled code that doesn't really look like this at all, but it's still readable and nice.
I mean, what Pietro is saying is that we are not handling this, but hopefully some upstream pass will normalize this situation. But I don't know. Yeah.
Maybe I'm overlooking something.
It's something to think about, but in general, what Pietro says might be. I mean, if this is reorganized by simplified CFG or someone like it in a way that where we have a nicer constraint. But yeah, I mean, it's something to think about. It's an interesting example.
So let me try to state my intuition in a more precise way. It's not like completely formal yet, but it's a little bit more like reasonable than just an intuition. So my point is, Ivan was trying to build an example where we had a conditional node that wasn't the if that we wanted to squash into the switch, but something before that. Okay, and so you have a conditional node, and it's only one of the two situations. Either that conditional node predicates something on the same value that the other if and the switch are predicating on, or it doesn't. If it doesn't, we don't care because we're not going to have new constraints, and all we said until now still works. If it checks conditions on the same variable, assuming the oracle about the value range is the same, we're gonna have like those constraints also propagate to the second if and switch in non-obvious ways, but all the ways I can think of are ways that allow simplified CFG to really scramble that part of the CFG in a much simpler way. That's like a better description of my intuition. I don't know if it was clear or just more confusing.
But the case 2 here, this edge will never be taken, right?
Yep.
It's right. So this is weird code. It's a bit weird code. I'm fine with not emitting great stuff if there is a case that's never emitted. It's weird code.
Also, if you think that this, I mean, no sane compiler would have emitted some CFG that, I mean, maybe a compiler that is not optimizing don't realize that it's dead code and leaves it there, but I don't know. It seems weird, like not very likely to be something that happens often in practice. That's I don't know. There's Jack.
But at least we do not. I mean, the nice thing is that we do not do anything wrong. I mean, we do nothing, but we do not do a wrong transformation. If this example would have led to a wrong transformation, I would have been. But yeah, it's an interesting example. Jack, you wanted to say something?
Like my basic, like I want to play a little bit the devil's advocate in the sense that so when stapling, we are okay with duplicating code if necessary. So if for example, in that example that you're just showing, we have a jump from somewhere else that jumps into return 1, 2, 3, we're okay with duplicating return 1, 2, 3. Is that correct?
It depends. What you're trying to do here is capturing a pattern that is common in code that is emitted by compilers. If you have another edging coming on return 1, 2, 3, I mean, it depends on what are the conditions. If maybe we can use that edge and staple it together, it depends what are the conditions on that edge. But I mean, in general, yes, I think that our general, what we want to do is basically say we should not duplicate unless there was a goto in the original code. That's where we would like to get at a certain point. If there was a goto in the original code, we're okay with duplicating. We can have a policy if we're going to duplicate too much, we don't do it, and we emit a goto. But if there was no goto in the original code, then we should think really hard if we can come up with transformations such as the one that we just described in order to better capture what was going on before and avoid gotos or duplication. That's the goal of the transformation.
Yeah, no, the way, at least, like, I think, the way I see it, maybe like the compiler does like
like you have a block of code that you've duplicated in the original code, but it's the same. So the compiler might say, I'll just put a jump and avoid having twice as much code. But I understand. The other thing that I was I'm a bit curious about is how you, like in this case, the example is straightforward in the sense that you have an if with the same value and then a switch on the same value. What if you have a situation where there is like a like they're not the same? Like at least here's something that I thought of. I'll just paste it in chat. Where I think it might it might get broken, because I assume that the compiler, like in this case, would go like if it's like if it's greater than it's less than 128 or 150, jump to default, and then it shifts the x down and then does a jump table. Like that's at least what I would expect it to do, and I guess that would like complicate things in the trying to figure out the default.
Okay. I want to persuade you that this is not perfect, but assuming that AVI is perfect, it's a good thing to do. So, depending on how good is AVI, I think we can handle the situation you're talking about or not. Depending on whether we have a good constraint on the right value, we can do it. So I would say what you're saying is probably true, but I would push that problem to AVI. I would say these algorithms, and this is the nice thing about conceptualizing oracles, that you can decouple things. You say AVI is my oracle. If AVI can give me good enough information, I'm gonna do a very good thing. But if not, go complain with the oracle. That's the kind of approach that we follow. Then maybe we can better discuss the example. We could also throw it at a compiler and see. But I think that the important thing here is I want to be persuaded that the transformation is correct, giving perfect information from the oracle. Okay, Pietro.
Yeah, I like a couple of words to add to what Jack said. So what you said, you are concerned. So at some point you said, so you're willing to duplicate the block if there is some edge coming there from somewhere else that is not involved in this transformation here, right? And I mean, I see why you're saying that, but at the same time, I kind of disagree in a sense that at this point we are not saying we are willing to I mean, we are fine with something being duplicated. What we are trying to do is more like there is a specific set of situations that can be matched to switches that are strictly superior with respect to the previous shape of the CFG. Okay, we're not saying and that we are not going to care about anything that is left out by this transformation, but whenever you have the opportunity to do this transformation, it is always correct and it is always strictly beneficial, because and what I mean by strictly beneficial is that it reduces duplication. It doesn't always remove it completely, but every time this transformation is triggered, you are saving at least a duplicated block in the decompiled code. And sorry, Ale, can you show the CFG again? 1 second, because I am not seeing it anymore.
1 sec.
So, like on this example, if you had another edge coming from outer space to return 1, 2, 3, you would still be able, like with constraints that don't match the optimization, you would still be able to apply the transformation as Ale described it on this CFG and turn it into a switch with a default. The only problem is that you would still have like the edge from outer space jumping to the default. But my point is, after the transformation, the block return 1, 2, 3 would be duplicated only once to break it out from the switch and leave a copy alone from the edge from outer space. While if you don't do the transformation here, you would end up with 3 copies of the block return 1, 2, 3, because one would be strictly belonging to the switch, the other one would be the children of the node x minus x less than 3, and the other clone would be like the child of the edge from outer space. So it's never detrimental, okay? And whenever it kicks in, it's correct. It doesn't mess with side effects, and it produces a CFG that has less opportunities for CFG restructuring to duplicate code. So there's no way not to do it. No reason not to do it.
It's like doctors, do no harm. Okay, other question, observations?
If no one has any CFG-related question, I have a more general one.
Go ahead.
About side effects of a load operation. If we know that load happens to some constant memory, that we know never change, that is read-only, and we actually know what the result of the load would be, what are the side? Why can't we remove it? What are the side effects that we are so afraid about from the side? Such, I don't know, maybe some clearly unchanged load from some register value, which we know because we can deduce it because it was said before this in the function. So there are no like unrelated, I don't know, no weird condition, just super simple load from a constant memory. What are the side effects? Why are we afraid to remove it?
Well, we cannot. I think the principle of easy transformation is that on all paths, before and after transformation, you should execute. You should not have any difference in terms of externally observable behavior. I mean, if the load was from, let's say that here you have a store. I mean,
yes,
you can.
Store is different.
Or if the load stack falls. I mean, I'm not saying that we are afraid. I'm just saying that it's better not to have it. It's better not to have it. If we do the transformation before, first of all, you don't have the load, and second of all, you don't have to make an optimization that takes away a load that runs a load on a path where before did not run. So you have the best of both worlds, But I mean, even if imagine if you were running the load here, on the no path, and x was 100. Maybe x is 100, and jump table plus 100 is mapped. So you're doing a load and you're not using the result. You're probably not.
I'm not suggesting to add loads. I'm like, what are the side effects? Because yeah, it could float, but we are already assuming the result because the whole transformation is based on the fact that we know that behind this memory location is this value based on the oracle or some other stuff. So we already assume the result of the load. So we already kind of act as if it didn't float. So what is the point of like preserving it if we already know how it should have gone? Because if it doesn't go as we assumed, it is already all broken.
But so you're not suggesting to run the load also on the no path?
I'm suggesting to remove the load outright because the side effects I cannot see the side effects that would like justify leaving it there. If it could possibly float, then everything is already broken because we are assuming the result.
But it depends. So you're saying that the code stays like this, so it's not like you want to run this load on both the yes and no paths. You don't want to run it on the no path. This is important for me to understand.
What I'm trying to say is we don't need this load at all. I don't see what kind of side effects would make us keep it in this case.
Okay, we can. No, but I understand that the load is superfluous, but you know that from a distinct analysis, from the analysis that we spoke before. In these situations, we did nothing to prove that the load, did anything. Those are two separate analyses. In this second analysis, we do not rely in any way on what the load does. We are just saying, the only thing I said is that if you run let's call the thing I spoke about in the first half of the presentation, optimization 1, and let's talk about the second one, optimization 2. Optimization 2 does not need to rely on the fact that that load is constant. We didn't say anything concerning that. But we said, if you run optimization 1 before, that load will disappear, and in optimization 2, things will be a bit nicer, and the load will not be there. But the fact that the load is loading from a constant range that is known as, let's say, a leaf time and all that stuff, we did not rely on that at all on optimization 2. And trying to think about that in optimization 2 will make it more complex with no benefits. I don't know if this makes sense.
Yeah, it's like we are thinking about different cutting points between. Yeah, I get your point. Thanks.
I mean, if you consider them all together, then I see your point. But I'd really like to consider these two transformations separately.
Oh, but wait. Doesn't this law, isn't the first transformation still kind of touches on this slot, doesn't it? So it still keeps it. Like in the first example, the slot was part of the switch. You didn't even draw a different node. It was just a switch. Switch was loading automatically. So when we are doing this transformation...
Sorry, what example are you talking about? You're talking about an old example?
In the very first graph, the slot was implied inside the switch. It wasn't even... I mean the graph with like the CG.
This one?
Yeah, the load is inside the switch. I mean, it's not even separated. So
yes.
It kind of does touch on it because it does assume the result. It does look at the operands and it does assume the result, doesn't it?
But the transformation I described without splitting is wrong. If you do not do the stapling, if you do the stapling, you have to staple only to the switch and nothing else. You cannot keep the load there. If you keep the load there, if you don't split the basic block, then the transformation is incorrect. It's not correct.
It's not what I mean, but yeah, let's go. I will just message in Mattermost what I mean, what I'm trying to say, because I need to draw it because I'm already confused about the concentration.
We need more graphics.
There's no point to continue discussing it like this, like without the like qualifying all the situation. Qualifying the situation.
All right. Anything else?
Apparently not.
I mean, I expected people. I mean, there is one last thing. You know, we are changing the CFG. What about fees? You know, if there are fees, we need to adjust them. You know, and I think there we need to think a bit more because maybe there might be some situations where we create something. I mean, we need to do something about fees, and it's possible that we need to inject. We are adding predecessors and we are removing predecessors, and we know there are some paths that will never take place. So it might be that in fees we might have some incoming undefs or stuff like that. But maybe that's a topic for another time. If there are no fees, this should work. Anyway, okay, I think this is enough.